we will start our classes in physics, and this lecture is an introductory lecture in general what we study in physics, and just to introduce you to some concepts without going in the details. So, first let us see, when we study science, in science what we do is, it is an attempt to understand natural phenomena. So, we have some event which occurs in nature and we try to understand this, and not only we try to understand this phenomena in detail, we also use the knowledge of this event and we try to predict, modify and control the phenomena. So, first we try to understand the phenomena and then we try to predict, modify and control the phenomena. So, a study in science is a typical study in, it starts with our exploration of events and then it leads us to some sort of an experimentation, where we try to repeat the events which we observe, or we try to create some events, and based on these we try to predict the events which take place, and then we try to modify them. Can we modify them as per our wishes and control the events? And in order to achieve all these, we have our power of observation, by which we observe the events, and then we use reasoning, and we also use mathematical modeling. This is an important part of our study, that we will try to use mathematical equations to describe physical phenomena. And from here, once we do these, this will lead us to formulation of some laws. Now, laws are some statements which we say about a particular phenomena, and we say a particular phenomena can be described by this law. Now, there is nothing sacrosanct about the laws. We make these laws on the basis of empirical observations, and then sometimes, as we will see, it is possible that the law may explain some phenomena, but it may not explain other phenomena, or sometimes it may be sufficient for a coarse explanation, but when we go into details or when we go in minute effects, then we find the law is not sufficient. So, that leads to modification of laws. So, these are basically, this is what we do, and that is what leads us to what we call as a scientific theory. So, our theory will consist of all these things: observation, reasoning, and this is how it will lead us to development of maybe some technological products based on some scientific observation. Now, for example, let us take the case of a pendulum. A mass is attached to a string and we tie it, and the pendulum swings. Now, we observe the time period of the pendulum, how far in, let us say, in a given time, how many oscillations it makes. Now, when this was first observed, then somebody observed that if you change the mass of the pendulum, it does not affect the time period. So, now the law which describes the time period, which may eventually come out as a formula, should be such that it does not contain mass of the bob. If mass is there, then we observe, our real life observation is that this oscillation time period is independent of the mass. So, therefore, the laws have to be such which describe the real life world in a realistic way, and then only we can say that the theory which we have developed is reasonable. So, now other thing which we will realize is that when we talk of science, then science is dynamic. Whatever theories we develop, they can be refined and made more accurate. So, and often for the theory to become more accurate, we may need more precise observations. Observations may be up to a particular precision, then you have a particular theory, but once you get more precise observations, then you will keep on getting maybe more refined theories. And an example of this is when we look at the theory of planetary motion. In 1500s, Copernicus came up with the theory of planetary motion, and what Copernicus said was that sun was at the center and planets went around the sun in circular orbits. So, Copernicus theory which was there said that the sun was at the center and planets travelled around in circular orbits. Now, so this was the theory, and then in late 1500s, Tycho Brahe made some observations. He studied planetary motion and collected the data. And based on Tycho Brahe's observation in early 1600s, Kepler examined this data and he came up with the laws of planetary motion, where he said that the planets moved around the sun in elliptic orbits. So, therefore, this is a case where based on the data the theory was refined. So, let us just complete this for this. So, Kepler in 1600s, this was early 1600s, he examined the data and refined Copernicus's model and stated that planets moved around the sun in elliptic orbits. So, now we also come across some cases where the existing theories cannot explain some phenomena, and therefore, then maybe the whole theory has to be modified. For example, we had the classical mechanics or Newtonian mechanics, which was used to study motion of particles. Then Euler modified this theory and extended this to include motion of rigid bodies and a set of particles. But classical mechanics was unable to explain the phenomena of atomic motion, and this the accepted wave theory of light was unable to explain the photoelectric effect, and this led to quantum mechanics. So, the journey which started from classical mechanics and based on Newton's laws, this was extended by Euler for rigid bodies, but this could not explain atomic motion, and this led to the development of quantum mechanics. There was experiment of Rutherford, which led to the nuclear model of the atom, and then came the model of atom by Niels Bohr in 1930. So, this quantum mechanics was something which came as a replacement for classical mechanics to study the atomic motion. And so, in certain cases the theories could be modified to explain some phenomena which have not been explained before. But in physics, basically what we study is a study of the physical world and the basic laws of nature, and how the laws of nature, how they are manifested in natural phenomena. So, a study of natural phenomena is what one can take as a basic description of physics, how we study things which occur in nature. So, study of the physics we can then define as, or we can think of physics as a study of the physical world and looking at the basic laws of nature, how they are manifested in the natural phenomena. So, that is what we will study in basics. Now, in physics, now there are two domains typically in physical in study of physics. One is what we call as the macroscopic or the large scale, and the second one is microscopic or small scale, and the small scale could be atomic, molecular or nuclear. So, now we have in physics, we have a branch of physics or certain subjects of physics which are covered under what we call classical physics, which basically largely we can think of these would be what would cover the macroscopic phenomena, motion of particles, set of particles, rigid or deformable, which is what we will study in mechanics. So, under the classical physics, the first subject which comes is mechanics, which is basically deals with motion of particles, either single particle or a set of particles, and then we also have motion of rigid or deformable bodies, and this branch of mechanics basically is based on equations which we will are referred to as either Newton's laws of motion or Euler's equations. So, that is what the classical mechanics which we study, movement of macroscopic particles, not at the atomic scale, at a large scale we have particles which are moving, how they will move, what governs the motion of these particles. The second subject which we typically study under classical physics is what is referred to as electrodynamics. In electrodynamics, we study electric and magnetic phenomena. So, here what we study is we study charges, electrical charges and magnetic fields. How we see charged and magnetic bodies. So, how a charged body when it moves, what are the different forces between charges, we will study under electrodynamics. Now, here this theory of electrodynamics mainly has been developed by many people, but among the major ones Coulomb, Oersted, Ampere, Faraday, and finally among the leaders we have Maxwell, who combined the theories of electromagnetic forces. So, and among the phenomena studied in electrodynamics would be motion of, so we would study things like motion of current carrying conductor in a magnetic field, or things like response of a circuit to an AC voltage, or the working of an antenna. Things like this would be studied under electrodynamics. Then in the classical realm of classical physics, we have the third branch, which is called optics, and optics involve phenomena involving light. So, study of telescopes, microscopes, color exhibited by films, all these are what would come under optics. So, optics deals with phenomena involving light. So, and then in the classical mechanics realm, we have the fourth branch, which we call thermodynamics. In thermodynamics, we study systems in macroscopic equilibrium. That means we will study things like changes in internal energy, temperature of a system, which take place through work, and transfer of heat. So, these are the typical disciplines in classical mechanics. Then we also the microscopic study of microscopic phenomena is, as we discussed earlier, which comes under the realm of quantum mechanics. Now, the range of physical quantities which we study in physics are enormous. The 2 or 3 physical quantities which we can think of, which we study, are things like mass, time, length, and if we look at the scales of these, then we have very wide scales or wide range of scales which are studied in physics. For example, let us see in the length scale, when we see the smallest length scale which would be the nuclear scale, would be something like 10 to the power of minus 15 or 16 meters. So, this is the nuclear scale, and on the other hand, this is one hand where we have very small ranges, and on the other hand we have astronomical phenomena like universe and galaxy. So, on this is the one end of the spectrum, and then we have very large scale which are the astronomical scales, and this is what we talk of size of the universe, and this typical length scale would be something like 10 to the power of 26 meters. Then if we look at the whole range starting from a very small scale, we go to a very wide scale. Similarly, when we look at the time scale, the time scales are equally wide, and in our phenomena which we study, we go from ranges like 10 to the power of minus 22 seconds to 10 to the power of 18 seconds, which are there. And when we look at mass, once again the mass scale is something like 10 to the power of minus 30 kg for an electron to 10 to the power of 55 kg for the universe. That means, when we study physics, we will look at phenomena involving very small scales to very large scales. All these phenomena would be covered in physics. Now, one of the insights which came in earlier, quantitative measurements were made, and they are very central to the study of science and physics. And one of the insights which came was that in physics, can we find some laws which are universal? We have all heard of Newton's law, and there is this story that Newton was sitting in apple fall, and that gave him an idea of the law of gravitation. Now, what did Newton discover when he saw this apple falling on the ground? Well, one observation which was made was that when something is under a free fall, it is attracted by the earth. So, the apple was attracted by the earth, and he was able to predict that force. But then what was great about Newton's understanding was that he realized the force by which the earth is pulling the apple towards itself, that force is the same by which the sun is pulling the earth to itself, so that because of the same nature of the force, the earth moves around the sun in an elliptical orbit. So, the force which causes the earth to move in an elliptical orbit around the sun is the same force because of which the apple is falling on the earth. And this revelation which Newton made, and that is the universal law which Newton came across, and this was the greatness of that whole observation, that the same phenomena, any two masses which you look at, where there is some force which is there, an attractive force between these two, and this is called the gravitational force, and by virtue of the mass of these two bodies, they apply an attractive force on each other, and this force is valid all across the universe as far as classical mechanics goes, whether it is between sun and the earth, or between apple and the earth, or the sun and the moon, the force is the same, and that was the beauty. So, when we try to look at it, there are different forces which arise, and we can call them, at least as our knowledge of physics goes today, we have 4 fundamental forces. So, there are 4 fundamental forces, and the first of these forces which we have discussed, This is called the gravitational force. Now, gravitational force, we will each of these in this introductory lecture, I will just look at the tell you about the different things. The details of these will follow in the course. So, here gravitational force is a force of mutual attraction between two bodies by virtue of their masses. So, whenever there are two bodies having mass, they will apply a gravitational force on each other, and gravitational force basically is an attractive force. Both the bodies tend to attract each other, and so this is one of the first basic forces we talk of is the gravitational force. And as we discussed, this force is the same between any two masses. The masses could be small or they could be large. And a gravitational force, like some other forces we will discuss, it does not require any medium. It acts at between two bodies even from a distance without contact. The second force, which is a fundamental force, is what is referred to as the electromagnetic force. Electromagnetic force is a force between charged particles. So, and if the charges are at rest, then this force is governed by what is termed as Coulomb's law, and once again the details of Coulomb's law we will go through once we come to that topic. Now, electromagnetic forces are between two charges. So, when we have two charges, the charges can be either positive or negative. So, there are two dual nature of charge. So, based on this force, electromagnetic force can either be attractive or repulsive. So, this could be, unlike the gravitational force which was only attractive, electromagnetic force can be either attractive or repulsive. And we talked of static charges, they are governed by Coulomb's law. Similarly, charges in motion produce magnetic fields and vice versa, a magnetic field gives rise to force on a moving charge. All these are basically covered under electromagnetic forces. And what it is observed is the electric and magnetic fields are inseparable. They go hand in hand, and that is why we have this term called the electromagnetic force. Now, electromagnetic forces, they also, like the gravitational forces, they act at a distance. So, we do not need any medium as long as there are two charges, even if they are not touching each other, the electromagnetic forces would act. Now, we have talked of these two basic forces. Now, if you compare the magnitude of these forces, then it is observed that the gravitational forces are much weaker than the electromagnetic forces. The electromagnetic forces in general are much stronger than the gravitational forces. Now, the electromagnetic forces, they dominate the phenomena at atomic and molecular scales. So, if we go to the atomic and molecular scales, we will find that the electromagnetic forces are very dominant, and they govern the laws of atoms and molecules. So, at the small scales, the electromagnetic forces are quite powerful and they act, and they can be attractive or repulsive. Now, in macroscopic bodies, when we see two large bodies, generally in an overall sense they are neutral as far as charges are concerned. Therefore, between the macroscopic bodies, you generally will not observe electromagnetic forces, and the gravitational forces therefore dominate. But when we look at it, we will look at the order of magnitude of all the forces once we complete all the four, and we will see that electromagnetic forces are much larger as compared to the gravitational forces. Then we have the third type of fundamental force, which is even stronger than the electromagnetic forces, and these are the strong nuclear forces. Some of you would have already studied what an atom consists of. Those who have not, we will be looking at these when we come to the structure of an atom. But in an atom, there is a heavy nucleus which we model at the center of the atom, which contains most of the mass of the atom, and which consists of protons and neutrons. The bulky part of the atom is in its center part called the nucleus, and around it the electrons revolve, which are negatively charged particles. So, now given the nature of electromagnetic forces, what one realizes is that if all the protons and neutrons are clubbed in the nucleus, then all the protons are positively charged. So, therefore, there must be some repulsive force among the protons. If there is a repulsive force among the protons which is fairly strong, then the nucleus cannot be stable, because then the nucleus would disintegrate because of the repulsive forces of the proton which exist among themselves. But then the reason why the nucleus is able to exist is because there is something even stronger, and that is called the strong nuclear forces, which exist between neutrons and protons, protons and protons, and neutrons and neutrons. So, in the nuclear particles which consist of protons and neutrons, we have very strong forces which are even stronger than the electrodynamic forces, and these forces are termed as strong nuclear forces, and these are what keep the nucleus together, otherwise the nucleus would become unstable and would disintegrate. So, this is what the whole concept of strong nuclear forces are. So, these forces are forces which bind protons and neutrons in a nucleus. And since these forces have to counteract the repulsive electrodynamic forces of the positive forces between protons, these forces have to be much stronger. So without this, without the strong nuclear forces, the nucleus, which consists of positive charged protons and neutral neutrons would disintegrate. And the range of operations of these forces, the range of operation of the nuclear forces is very small, even smaller than the atomic scale, and this is of the order of 10 to the power of minus 16 meters. And the strong nuclear forces are not observed among the electrons. Then we have a fourth class of forces, fundamental forces, which we call as weak nuclear forces. Now, weak nuclear forces, they appear in certain nuclear processes, and there is a process called beta decay of nucleus, and where the nucleus emits an electron and an uncharged particle called a neutrino, and it is here that one in processes like this one observes weak nuclear forces. Now, these forces are not, they are stronger than the gravitational forces, but they are much weaker than the strong nuclear forces. So, they are stronger than gravitational forces, but much weaker than strong nuclear forces. So, if one tries to look at the relative strengths of these forces, then the strongest among them are the strong nuclear force, and let us say if this has an order of magnitude of 1, then if we look at electromagnetic forces, they have an order of magnitude of 10 to the power of minus 2. That means, the electromagnetic forces are 100th time that of a strong nuclear forces. And then if we look at the weak nuclear forces, the weak nuclear forces have an order of magnitude of 10 to the power of minus 13, and the gravitational forces, which we said were the weakest, they have an order of magnitude of 10 to the power of minus 39. Now, the range of forces, range where these act, the gravitational force and the electromagnetic forces, they act on all ranges starting from infinite length scale to closed length scales, whereas the nuclear forces, they act in the range of 10 to the power of minus 15 meters or so. So, the two nuclear forces act on very, very small ranges, whereas the other, the gravitational and the electromagnetic forces, they will act on all scales. Now, given these four sort of theories, then there is, as we there is a trying to, can we unify these theories into one. And when we talk of unified theories, the best example of unification, the first example was provided by Newton, where he unified the celestial and terrestrial mechanics into one. Whatever phenomena we observe between particles, when a ball is thrown, when we see the forces, the force with which an apple comes towards the earth is the same by which the earth rotates around the sun. So, this was one of the ways where the forces were unified. So, physicists are always looking for a unification. Can we find a theory by one theory if all the forces can be explained? So, another landmark which one can say, which came in the unification of, so when we talk of unification of forces, let us list these down. The first one, as we said, was done by Newton, where he said that the celestial and terrestrial mechanics governed by the same force. The next theory which came in unification was provided by Maxwell, and what Maxwell did was he unified electricity, magnetism and optics. And basically he came with the postulate that light is an electromagnetic wave. So, with that postulate he was able to work out a unified theory. Then recently there is a theory which theory by Salam, Glashow and Weinberg, and this theory talks of unification of weak nuclear forces are seen as the same aspect of a single electroweak force. So, there is some sort of a unification of weak nuclear forces and electrodynamic forces by these theories. Now, the details of this again, as and when you will need, would be seen when we come to this. Now, one of the things which we have when we will study physics and which holds everything together, we come across similar laws, and these are termed as conservation laws. We have certain quantities which we will define. We will have a law termed as conservation of mass. Now, as far as macroscopic physics went, the law of conservation of mass says that mass is always conserved, mass cannot be created or destroyed. And it turned out to be a law, to be a reasonable law, and is still a reasonable law, but till we go to the atomic scales or nuclear scales, where when we have a nuclear reaction, then we say that mass could be converted to energy. But as long as we are away from that realm, then conservation of mass is a reasonably valid law, and in terms of classical mechanics, we still believe it to be a law which exists. Of course, when we study nuclear reactions, then we have Einstein's theory that mass can be converted to energy, and then this does not hold. But otherwise, mass conservation is one of the most basic laws. Then we also have laws for conservation of energy, conservation of linear momentum and conservation of angular momentum. Now, we have to be careful when we talk of conservation laws, because in a wide sense, when you talk of conservation of energy, then if we are looking at a mechanical system and we have things like, which we will explain, kinetic energy and potential energy, then we say that energy is conserved. Then this comes with a particular meaning. We have to ensure that there is that work done, whichever work is being done is only being done by mechanical forces. There is no loss of energy due to heat and other things. But once we study this under the realm of thermodynamics, then we will say for a given system, if the system is isolated, then energy is conserved. So, when we study these conservation laws, we have to be careful, we have to see the laws from where the conservation laws are being derived, and then we will study them. So, again the details of these, right now we are just seeing a flavor of some of these things, the details will come as we study this. Now, the last thing which I want to discuss today is, in a lot of phenomena when we study in physics, we have two things which will come, a system and the surroundings. Most of our study in physics is geared to something which we want to study. Let us think of a car, we want to study motion of a car. So, we will look at the car, and the car is what we will call as the system, and we isolate it from everything which is around the car, and we will call that as the surroundings. And then our study of science today often concentrates on the system. So, we look at the system and we study how the system behaves. We may be looking at the motion of the system, we may be looking at the heat content of the system, the temperature of the system, but we focus on the system. But system cannot exist without surroundings, the surroundings will be there. So, what we have to do is, when we isolate the system, the effect of the surroundings are put in as some sort of a model. And for example, when we study mechanics, then we concentrate on the system and we draw what is called a free body diagram, where we isolate the system from the surroundings, and the effect of the surroundings in mechanics problems, we will put it as force or moments which are put on the system because of the surroundings. Now, in such a study, while this has led to a lot of development, but some of our woes of modern science are also because of this. Because when we study the system, we want the system to be perfect and we forget the surroundings. For example, take the example of car. If the car is our system, we want a car which accelerates, which moves with great speeds, which can accelerate from 0 to 100 miles per hour in 2 seconds. So, we design things in the car which does all of that, but what we forget is what it is doing to the surroundings, and sometimes these are what lead to the problems which we have caused in the world for ourselves. And maybe when we isolate the system from the surroundings, we also have to model what the system is doing to the surroundings and design that also properly. I think with that note, we will end today's lecture and we will continue from here in the next class.